Okay, so good afternoon to everybody. So welcome to this joint webinar, CG Shine and Times. I guess you all know me, so I'm Davide Dardari from the University of Bologna, and the title of this webinar is Over-the-Air Electromagnetic Signal Processing for Next Generation Wireless Networks. Well, so you all know that one of the key aspects of CG will be the fusion of the digital and the physical worlds. So that will enable a lot of new application or enhance existing application, such as extended reality, digital twinning, holographic video, and so on. And obviously, these new applications require a huge amount of traffic so that the new wireless networks, next generation wireless networks, will be able to support a huge amount of traffic. But at the same time, we have a lot of constraints in terms of energy consumption, bandwidth, reliability, latency. So, among the several solutions that has been studied in order to solve this problem, for sure, what we learn about MIMO system is that if we increase the number of antennas in a MIMO link, so we gain in spatial multiplexing, so we increase the capacity actually. So that if we look at what happened moving from 4G, in which we had more or less a few antennas per base station. In 5G, we have 100, let's say, antenna per base station. So we expect to break the barrier of 1,000 antenna in a one base station in CG. So a huge number of antennas. So that we are moving towards what is called extremely large antenna arrays or extremely large MIMO system. So having a lot of antennas brings advantages not only in terms of, let's say, spatial multiplexing capacity, but in general, if we combine the adoption of a large number of antennas and the use of high frequency bands, for instance, millimeter waves or sub-terahertz and terahertz, it is very likely that, especially in indoor scenario, that the users are located in the near field region of the base station or the access points. So near field means that on the one hand, several models that people like me working in signal processing and communication theory are, let's say, currently using fail because they are based on plane wave, let's say, propagation, so they have to be revised. But at the same time, we might gain some advantages in terms, for instance, of beam focusing. In the near field, we can perform beam focusing. We can have also high rank line of sight communication. That means it is possible to exploit spatial multiplexing even when we have a very strong line of sight, let's say, component in the communication, whereas in a far field, the rank of the channel is basically one. But also we expect gains in terms of positioning. For instance, we might position or infer the position of a user using just one antenna, because exploiting the curvature of the electromagnetic wave in near field, we can infer using just one antenna, not only the angle variable of the signal, but also the distance. So in other words, the position. So there are a lot of advantages when moving from a low number of antennas and a large number of antennas. But obviously we have several challenges. And so we know that the main challenge is the digital bottleneck. So we know that after the publication of Shannon landmark paper in 1948, so the digital revolution accelerated. So we moved from a world which was based mainly on analog signal processing to a world in which basically everything is done, almost everything is done in a digital domain. So in particular, for what regard the communication systems, now thanks to software-defined radio platform, we are moving the border between the digital domain and analog domain closer and closer to the antenna. Obviously, this is very good from the flexibility point of view, because we have all the gains in working in the digital domain, but at the same time, the current few digital hybrid implementation of signal processing tasks when going up with the number of antennas, especially if you work at high frequency, we might face high power consumption, increased latency and size. So what is called digital bottleneck. Well, just to make you an example, so suppose that we get a full digital MIMO architecture, in which we suppose we have a large number of antenna elements. So we have antenna arrays with a large N. So full digital means that we have one RF chain, so one digital to analog converter, or the receiver analog to digital converter, and also the RF chain for each antenna. Okay, so if n large, we have a huge number of this RF chain. And everything is done in the digital domain. So obviously, this solution is that one providing the maximum flexibility, but at the same time, we expect a high complexity, high power consumption, and also potentially high latency in processing, because the processing takes place in the digital domain, and also the power consumption of the digital processing part, for instance, the power consumption of FPGA. So this is good from the, let's say, performance point of view, but from the scalability point of view is not so good. Obviously, you know that in the last decades, several let's say, solution has been studied. I just mentioned the hybrid MIMO architecture, which will reduce a lot of the number of RF chain, for instance, up to NA, by keeping large N. And so we perform some processing in the analog domain using phase shifter, for instance, so that we reduce the complexity, the energy consumption, and also some latency. So in particular, we reduce the power consumption because we reduce the number of RF chain, but the price we pay is that if we use the phase shifter, so we have reduced flexibility in performing what we want in terms of processing. And also, as I'm going to show you in a very simple example, the next slide, when N is very, very, very large, also the hybrid architecture might lead to some energy consumption issue. So in this table, so don't worry about the numbers. So here I just put the typical values for what regard the power consumption for all the elements composing the RF chains and the phase shifters. So let's just focus on the red numbers. So the red number, first one refer to the rough estimation power of a full digital architecture employing 1028 antennas. So here we see that we need almost 13,000 watts, a huge amount of power. But even though we lower the number of RF chain using a hybrid solution, but still with the same number of antennas, so also in this case, well, we reduce a lot, one more domain to know at least the power consumption, but it's still not so negligible. In particular, if we make the same exercise by further increasing the number of antennas, also the power consumption of the phase shifter splitter might increase. And here, all the power consumption due to the digital processing is not accounted for. Okay, so if we include also the digital processing, all this number might increase significantly. So just to say that in general, when the number of antennas become very, very large, current technology, current architectures might not be scalable in terms of complexity, power consumption, latency. So basically, we might have a performance and sustainability issues. So that means we need for a paradigm change. And one possibility is to shift part of the signal processing directly at the electromagnetic level. So by finding sort of a balance between what we do in the digital domain and the analog domain in order to minimize or to mitigate the power consumption, the latency, but at the same time by keeping reasonable performance. And so this is quite a hot topic today, which is referred to as wave-based signal processing or over-the-air electromagnetic signal processing, and so on. So holographic MIMO, so there are several names that more or less indicate the same thing. Well, but what do I mean with the over-the-air electromagnetic processing? In particular, I refer to the case where we have a generic electromagnetic structure composed of a large number of passive, almost passive, and almost lossless reconfigurable scatters that interact in the rectilinear field. So all these stuff are coupled, okay? And we can change the way each scatter can behave through a set of parameter theta, which is the parameter we can use to configure this electromagnetic structure. So that supposing we have an impinging wave from the left, by properly configuring all these, the way these elements interact with the electromagnetic wave and each other, then we get a reflected transform electromagnetic wave according to some desired result. So that if all these stuff are almost passive, we have a high energy efficiency, so we can increase N a lot, so the number of elements to very high level without increasing too much energy consumption, because the only energy consumption we have here is just for the control signals. And at the same time, we have almost zero latency, because all the processing, so the electromagnetic transformation takes place at the speed of light, and also in general lower complexity compared to other architectures. But how to use this, let's say, very generic, structure? So we can see two possible scenarios. So one scenario is this one, in which we have some sources, for instance, a transmitter with several antennas or several transmitters. And far away, we locate one or more electromagnetic structure, that can be configured. Far away means in the radiative near or far field with respect to the sources. And again, far away, we have a receiver space. So a space in which we observe the results in terms of electromagnetic field. So the receiver space could be one receiver, actually, with multiple antenna, for instance, or can be the union of several spaces, several users with one or more antenna each. Well, the purpose of this scenario is to deploy this kind of electromagnetic structure with low complexity structures in order to change how the propagation behaves. So the behavior of the propagation, so toward the smart radio environments paradigm. And so to change the propagation conditions in order to obtain, to increase the coverage or to increase the rank of the channel and so on and so forth. So within this scenario, we can find a very popular, let's say, technology, in particular, configure intelligent surfaces. The RIS can be seen as a possible technology to realize this scenario, but there are also others like metaprism, self-conjugated metal surfaces, and so on. But today, I would like to focus more on the second scenario, which is a little bit less investigated than the first one, in which now we move the sources very, very close to the electromagnetic structure, so ideally in direct linear field, so that we have a complete coupling between all these elements, and with the purpose to reduce possibly the number of active sources. So each source typically is connected to an RF chain, so that you would like to reduce the number of RF chain, for instance. And this is a typical scenario of a base station of an access point. So this could be the end part of an access point or of a base station. In this example, we have a transmitting, but we can also, let's say, reverse everything and think about the receiver. So everything can be also done at the receiver side. Well, within this scenario, we see several technology possibilities. One is the electrical steerable passive array radiator, so XPAR, stack intelligent metasurfaces, dynamic metasurface antenna, dynamic scattering arrays, and so on and so forth. And the next, I would like to focus more on these two, so the stack intelligent metasurfaces and the dynamic scattering arrays. Well, but the idea is not new, actually, because the idea of putting very close to the an active antenna several reconfigurable passive antenna elements dates back to 1978. So this, let's say, seminal paper by Roger Harrington, who conceived this idea to put an active antenna, just for instance a dipole, surrounded by a certain number of dipoles. Each one is loaded by a reactive load that can be changed, so that by properly tuning the reactive load of each of these passive elements, we can shape the radiation diagram, so that we can obtain a dynamical, let's say, beamforming by using just one active element, so just one RF chain. So this is quite convenient from the energy consumption and complexity point of view, because the counterpart would be the use of a phase array in which we have all these elements are active, and we have phase shifter to be attached to each of these antenna and properly, let's say, designed, so that this leads to lower consumption solution. And today, this idea is known as SPAR, actually, so it has been investigated as SPAR. But let's keep our discussion more at for a while at a very say technology agnostic level. So let's try to understand what is the final goal of this. So the final goal is to use this configuration in order to obtain a multifunctional electromagnetic signal processing using this, I say, almost passive electromagnetic structure. So suppose that the number of scattering elements is very, very large, because we would like to obtain an electrically large structure, as I mentioned at the beginning of the talk. But at the same time, we want to keep the number of active sources as low as possible in order to minimize the RF chain. And one possibility is the following, so is to design the parameters actually of this structure such a way to each input, to each active source, so x1, x2, and so on, we can associate a different spatial signature observing the receiver space. So F1R is the spatial evolution of the electrical field associated to x1. So F2R is a different spatial, say, signature of the electromagnetic field associated with x2, and so on and so forth. We have a linear combination of this input, and where each input provides different results in the spatial domain on the receiver space. But what is challenging is that we would like to obtain this, let's say, multifunctional results using the same configuration. So we would like to find the configuration theta in such a way simultaneously we obtain these different responses, each one associated with a different input. So we have a multifunctional electromagnetic signal processing. Okay, so this is the, let's say, the final goal of this structure. So before diving into a technology example, so the stack intelligent metal surfaces and the dynamic scattering arrays, it is important to understand what are the theoretical fundamental limits in terms of processing of this kind of structure. So obviously there are fundamental limits. So it is important to understand how these limits in particular are related to the size of the device. So let's start from this situation. First of all, I would like to point out that the fundamental limits will be explained in terms of number of degree of freedom, where the number of degree of freedom of the receiver space represent the minimum number of parameters that are needed to approximate any physical consistent field, ER here, defined in this receiver space up to arbitrary precision. Okay. In general, the number of degree of freedom is not finite, so it is an infinite number. But if we depend on the geometry, actually the dominant, let's say, degree of freedom, the number of degree of freedom is limited. Okay, so we would like to find this number. Supposing that this electrical field is the result of the scattering of this electromagnetic structure, I showed you before, depending on theta. So a key question is to determine the signal processing capability of this electromagnetic structure in approximating any response here in the receiver space. So in other words, the degree of freedom, the number degree of freedom that this processing structure can manage, okay, by changing the set of parameters. It is obvious that if the number degree of freedom of the receiver space is 10, let's say, and we discover that the number degree of freedom of the electromagnetic structure is 5, there is no story. So there is no way to approximate any function here using this electromagnetic structure. Vice versa, if the number of degree of freedom of the electromagnetic structure is equal or larger than the number of degree of freedom of the receiver space, we have some possibility that we can actually approximate any function in the receiver space by playing with the parameter theta. Okay. Well, so as a first step, let's find what is the bottleneck. So supposing that we would like to understand what is the number degree of freedom, the maximum number degree of freedom this electromagnetic structure can manage, supposing that the receiver space is occupy the entire space, actually. Okay, so is unlimited. Okay. So supposing that the receiver, the observation space is the unbounded space, basically is unlimited. The number degree of freedom of the electromagnetic structure is still limited, and depends on the whether the structure is linear or two-dimensional, three-dimensional. So getting let's say using the fundamental result of antenna theory, it can be found that in case of a linear structure, a one-dimensional structure, the number degree of freedom is given by this expression. Basically, depends on the ratio between the dimension of this structure and lambda. Lambda is the wavelength. So it depends on the electrical size of the electromagnetic structure. So this ratio. If we move from one dimension to two dimension, for instance, surface, then we see that the number degree of freedom still depends on the ratio d over lambda on the electrical side of the antenna, but now we have the square. Okay, so we have a significant increase of the number degree of freedom moving from one dimension to two dimension. And then if we go 3D, so we consider volumetric structure. Unfortunately, we don't have a third here, so we don't have the power 3, but we still have a dependence on the square of the electrical size, but we gain just a pi compared to the previous one. So there is no significant gain moving from 2D to three-dimensional structure. So in any case, the message we can take away from this slide is that the number degree of freedom of electromagnetic structure in the unbounded space is limited by the electrical size of the structure. So it is limited by the ratio between the physical size of the structure and the wavelength. But obviously, we are not working in the unbounded space, so we have also a receiver or more receivers. So let's see what happens if we have a finite receiver. And for simplicity, I'm considering very simple geometry in which we have a surface structure, so two-dimensional structure. The first one dimension dt, the second one, the receiver structure dimension dr, and for simplicity, suppose that they are in parallaxial configuration. So, and the distance between these two surfaces is assumed to be larger than the maximum dimension of each of them. Well, under this very simple geometric setup, it can be found analytically what is the number of degree of freedom. So the number of degree of freedom is given by this expression that can be also derived using, say, elementary results of diffraction theory. But if we manage a little bit this expression, we can recognize that the number degree of freedom of this, let's say, this link is given by the number degree of freedom in an unbounded space of this structure the number of degree of freedom in the unbounded space of this structure, so what we have seen in the previous slide, multiplied by this term, which depends on the ratio between the distance and lambda. So that as long as we increase the distance, so all this term decreases, so we decrease the number of degree of freedom, and in particular, the number of degree of freedom goes to 1, decreases to 1 as long as we move in the far field. So that is a well-known result, for instance, in MIMO theory, in which we know that in a free space, here we are considering free space, when we are working in the far field, the rank of the channel is 1. So in this case, the rank corresponds to the degree of freedom is 1. Okay. In any case, all this expression is always bounded by the degree of freedom of the first structure, the minimum between the degree of freedom of this structure and the minimum of the degree of freedom of the second structure. Okay, so this is actually the upper bound on this. We can ameliorate the situation in case we are not in free space, but we have several scattering elements, so that if we have a geometry in such a way, we increase the angle of view of the transmitter from the point of view of the receiver because of the scattering, then this term can be increased with respect to the free space, so that we obtain a higher degree of freedom even in far field. In any case, this bound is still valid. Okay, and this is another well result in MIMO theory, which we know that a MIMO system typically provides a spatial multiplexing capabilities in rich scattering scenario. Well, so these are the theoretical limits, and then we understood that basically the electrical size of the devices determine the fundamental limits in terms of degree of freedom, so that on the capability of approximating any function, in particular at the receiver space. So now let's focus on two examples of technologies that can realize the scenario I explained before. So the first one is tech intelligent metasurfaces. So this is quite recent, let's say, technology that has attracted a lot of attention. Briefly, what is a stack intelligent metasurface? So suppose that we have a certain number of RF chain, for instance, NA RF chain, each one connected to an active antenna. First, we have the digital processing, signal processing case. And then in the near field of this active antenna, we put several RIS, so several reconfigurable intelligent surfaces that are transmitting. So that means instead of reflecting, they transmit on the other side. Okay, each RIS is composed of typically large number M of metatoms, and then we can, in general, design through a controller what is the phase shift introduced by each metatom in each layer. Okay, so we have a certain number of layers, and we suppose, in a very simple modeling, we suppose that the propagation takes place only from the left to the right. So we have only, let's say, forward electromagnetic propagation, so that we don't have interaction between previous layers. And the last layer is what is called the radiating layer, so that the last layer is devoted to the radiation, the final radiation of the electromagnetic field. So that the electromagnetic field, while let's say passing through the several layers, depending on how these layers are configured, the electromagnetic field is changed, so is transformed, and then we obtain, for instance, the desired radiated field. A very simple way to model SIM is the following. So we suppose that this RIS diagonal. Diagonal means that there is no coupling between the elements. This is a typical assumption for RIS, so that we can model the transmission matrix of each RIS as a diagonal matrix, where the phi1, phi2 are complex number, and we can change, for instance, the phase of the complex numbers. Whereas the matrix WL is the matrix which accounts for the coupling between the generic metatom in one layer to another generic metatom in the subsequent layer. Okay, for instance, using radial Sommerfeld diffraction theory, we can determine the elements of this matrix. So W1 to up to L are fixed. So once we fix the geometry, they are fixed. So it depends on the geometry, depend on the electromagnetic parameters. Whereas we can control the phase shifts introduced by each RIS. So that if you put all together, the end-to-end transmission matrix is just the multiplication of all these matrices, so W1, Phi1, W2, Phi2, and so on, up to the last one. This is true because we are assuming that the propagation takes place only in one direction, otherwise this expression will be completely wrong. Okay. And then the one possible design problem is the following, which we would like to determine which is the set of parameters of the RIS in all layers. We should consider if we want to have an end-to-end response matrix, which is as much as close as possible to a target response matrix. Okay, so this is the Fronebus norm, so that which indicates basically the difference between these two matrices. So that this is one possible optimization problem. So actually, it's not a simple problem because the number of parameters is in the order of the number of layers times the number of metaatoms, and also we have the constraints on the fact that the elements of matrix phi have unitary modulus. Okay, so we can change only the phases. So that is very complicated problem. But thanks to the particular structure, so if you look at this structure, so this is very similar to the structure of a deep neural network. So that some researchers have noticed this and have proposed a way to minimize this problem, to solve this problem by using the typical approaches that are adopted in deep neural networks. For instance, gradient descent algorithm based on error back propagation by calculating all the derivatives, according to the some loss function. So the particular structure of the SIM is particularly useful in order to simplify the optimization problem by borrowing techniques from deep neural networks. So that this structure has been studied to solve several problems in the literature, for instance, to perform wave-based beamforming, integrated sensor communication, particular direction of arrival estimation, etc. And let me just show here an example, which is very, very nice, of this kind of structure used as a deep neural network. Okay, so not only consider deep neural network as an inspiring technology to solve the optimization problem of the SIM, but also using the SIM to realize an energy efficient deep neural network. So this is an example in which we have the problem of classifying numbers. These are electromagnetic images. Okay, so the input layer, and in this paper, they demonstrated also experimentally that it is possible to use the SIM plus some nonlinear stuff at the end, and otherwise, it is impossible to have a classification. So that depending on the number we have here, the different pixel will change the color. So this is quite very promising if you want to reduce the complexity and in particular the power consumption. Well, so another example, the second example is dynamic scattering arrays. So we can think about dynamic scattering arrays as a generalization of the SPAR technology and the SIM technology, where again we have a certain number of RF chain, NA in particular, and each RF chain is connected to an active antenna element, and then these active elements are surrounded by a cloud of many passive reconfigurable scatterers. Such a way, all these elements are coupled, so they interact in the near field. And then compared to the SIM, here all these elements contribute both to the processing, to the transformation of the electromagnetic field, and at the same time to the radiation. Okay, so remember that in the SIM case, only the last layer radiates. So these intermediate, the hidden layers are hidden. So that means they just modify the electromagnetic field, but they do not radiate. Whereas here, everything radiates. So that's why this can be considered as a sort of generalization of the previous technologies. Well, let's see how to model, some details about the modeling. So in general, we can think about this element as a dipoles, for instance, half-wave dipoles. In particular, also the reconfigurable scattering elements can be a dipole in which we have a load. Ideally, we have a reactive load, so this can be a reactive load, and then we can change, by changing the parameter theta, the value of the reactive load. Why reactive? Because so that we don't have any power dissipation, but this is just ideally. Okay. So suppose that we have NS scatterers and we have Na active elements. The structure can have any shape, so it can be a two-dimensional structure, can be a three-dimensional structure. So this is very general setup. Well, so it is possible to derive the input impedance matrix of the DSA. So here we have Na inputs ports actually. What is interesting is that this matrix, which is the impedance matrix of the structure, doesn't depend on theta, on the configuration, so that this can be designed offline, basically, or can be derived by means of electromagnetic simulations in order to better take into account for realistic conditions. But the input impedance matrix depends on theta, obviously, because if we change the loads, we change also the input impedance. That translated into the need for inserting here a power matching network in order to maximize the power transfer between the RF chain and the DSA. And ideally, the power matching network should be lossless, and this should depend on theta, because if we change the input impedance by means of theta, then also the power matching network should change. So this is a very challenging aspect of this technology. I will show you later that it is possible to remove this complex shape block. And then we have the RF chain. In particular, we can imagine to have some digital processing, but now the digital processing works using a limited number of outputs, Na. Okay, so X is the input vector containing the information. Well, so this is a very general model. So if you put all together, we can write a relationship between the input signal and the overall currents that flow both in the active elements and the scattering elements, I, where WD is the matrix accounting for optional, let's say, digital processing, and the matrix WEM accounts for the electromagnetic processing. In particular, depends on how the DSA is configured, and this is the expression. So depends on the parameter theta. So if we change the parameter theta, so that means we change the values of the loads, then we change the way we process the signal. But I is represent the currents in the transmitting antenna, so it is of interest to see what happens to the receiver. Okay, so that it is of interest to derive the end-to-end model, so from the transmitter and the receiver. So this is what is done in the next slide, in which we consider a generic DSA transmitter, and we're supposed to take K observation point, K test point, in which we observe the receiver signal, for instance. Okay, then generic position. Okay, very simple. So Y is the observed vector. This is an example of possible geometric deployment of the scatterers, in which we have, for instance, two active antennas surrounded by scatter elements that are deployed in as rings, so increasing rings and in different levels. Okay, so that we have a 3D structure. So this is particular appealing geometrical structure because of the symmetry we have in the problem. I'll show you a couple of numerical examples of this. So again, supposing that we know the channel, so AC is the transimpedance matrix of the radio channel, which accounts for the propagation effects. AC can be evaluated analytically in free space, whereas can be estimated in more realistic scenarios. Then it is possible to write the end-to-end channel matrix, which put in relationship the input signal X and the observed signal Y, the receiver, where H is the end-to-end baseband equivalent channel matrix, which depends on the parameter theta, so the electromagnetic processing, and the matrix WD is a digital process. So that we can change this relationship by properly designing theta and WD. And this is the next point, so the joint optimization of the DSA and digital processor. Suppose that our target is to realize a different response associated to each input. As I showed you before at the beginning, also, we would like to obtain a multifunctional behavior of the electromagnetic structure, so that, for instance, H1 represents the end-to-end channel vector, which put in relationship with the X1, so the first input, to the K test points, so the field observing the K test points. So H2 represents the end-to-end channel vector linking the second input X2 to all the outputs Y, and so on and so forth. So we collect all these vectors in the matrix H-opt. So the H-opt is the desired multifunctional behavior we would like to obtain, and the problem is the following. So the problem is to find what is the set of parameters of the DSA electromagnetic processing, and if present, the parameters of digital processing in such a way that, and this is the end-to-end channel actually, is close as much as possible to the desired target end-to-end channel matrix. Okay, we have also a constraint. This constraint is related to keep the transmitted power fixed. Okay, so I would not focus on how to solve this. So this can be solved in several ways. For instance, using alternating approach, but this is still an open problem. How to find a very effective optimization problem, because this problem is nonlinear, is non-convex, and here we cannot exploit in general the techniques that has been used for SIM. Okay, so this is one of the main drawback of this technology. But let's see some examples, some numerical examples. So the first example is related to superdirective beamforming. Here we have just one input, one RF chain, one active antenna, and here we have 5 rings composed of 121 scatterers that are dipoles at 28 gigahertz, so that the total size of this is just 3.2 centimeters, so is a disk of 3.2 centimeter, and all these scatterers are put at about lambda over 4 distance. So why lambda over 4? So lambda over 4 is a sort of magic number. So we found out that using lower distance, so lower than lambda over 4, we increase the coupling between the elements, but at the same time we decrease the degree of freedom we have in designing the desired behavior. On the other hand, if we increase this distance beyond the lambda over 4, we decrease the coupling, and this decreasing of the coupling decreases the possibility of let's say, modifying the electromagnetic field. So this lambda over 4 is a magic number we found out through electromagnetic simulations. So this structure has been designed in order to obtain a beamforming toward 4 different directions. Okay, so from 0 to 90 degrees. And this is the result. Well, so we have quite nice beams that are symmetric. So that means they are have the same shape, and we have quite low side lobes. What is interesting is to compare this result with classical antenna arrays, for instance, uniform linear array with active elements. So for a fair comparison, here we have considered 6 elements so that the aperture is the same of this. Okay, these are 6 active antennas. So here we have only 1 active antennas, and this is the radiation diagram. Obviously, this is a classical radiation diagram of a linear array. So as we know from antenna theory, that as long as we move toward the 90 degrees, the shape, the beam degrades. Okay. Obviously, if we consider a uniform circular array, we don't have this with the degradation. So we have still have symmetric, let's say, lobes. So this is again, we have 36 active elements in order to keep the diameter comparable to that one. So here we have instead of 1 active element. But the good news is the following: is that here the gain we obtain is 18.60 dB, which is 80 dBs more than the classical uniform linear array, and almost 3 dB more than the uniform circular array. What is the meaning of this? The meaning is that we have obtained a superdirectivity effect. Okay, perhaps many of you know that typically it is possible to obtain a superdirectivity effects only in an array, only in the end-fire direction, okay? No, not in all direction. Here we obtain a superdirectivity effect in all directions. Okay. So this is one interesting, let's say, result in using this structure by using basically only 1 active element. The second example is multi-user meso. So we have 4 users with the same. We suppose that we have the same structure, but now we have 4 active elements because we have 1 RF chain per user, because we would like to send data x1 to user x1, user 1, x2 to user 2, and so on and so forth. And what is the purpose here? The purpose is to find what is the configuration of this DSA, so the parameters theta, in such a way we have simultaneously 4 beams, each one towards the user, according to zero forcing design, in such a way these beams are orthogonal, so there is no interference or coupling between these 4 users. And this is the result, so don't worry, this is a quite complicated plot, but let's focus on the red diagram. So the red diagram is the radiation diagram associated with the x1. Obviously, this points toward user 1, but it is quite easy to notice that in the direction of user 2, 3, and 4, the red radiation diagram has nulls. So there is no interference, basically. And the same applies for the others. So we obtained a multifunctional result. So we have a different, say, electromagnetic response associated with each input, okay, simultaneously with the same configuration. So there is no one configuration for user 1, user 2, and so on. This is the same configuration. Simultaneously, we have this result. And the last example I show you is a multi-layer MIMO electromagnetic precoder. So again, using the same structure, the idea is to avoid performing the precoding in a MIMO system, which is typically done in the digital domain. For instance, we have to implement on, let's say, on FPGA, a matrix multiplication, okay? And if the number of antennas is very, very large, so that means also the matrices are very, very large. Okay? So we avoid completely this processing in the digital domain, and we would like to obtain the same results using at the electromagnetic level, so using this structure. So supposing this example to have a multiple channel with having rank 4. So we know from MIMO theory that if the channel has rank 4, realize up to 4 layers. So we have a spatial multiplexing of 4. So we can establish 4 orthogonal links from the transmitter to the receiver, supposing that the receiver is conventional MIMO receiver with the combiner. Okay. Well, the idea is to find which is the configuration of this DSA in such a way realize the precoding matrix. So the precoding matrix can be found supposing to have estimated the channel, so by means of a single variable composition of the channel. So V is from the theoretical point of view, MIMO theory, we know that V is the precoding matrix we should implement in the transmitter. So the idea is to design the DSA in such a way the electromagnetic processing is equal or as much as close as possible to the matrix V. So find what is the theta, such a way we have a good approximation of V, the precoding. So this is possible, and this is the result. So what we see here is the final diagonalized channel matrix after the precoding combining. Ideally, this matrix should be an identity, okay? Should be diagonal, okay? Ideally, well, it's not very far from to be diagonal, because if you look at these numbers, these are in dB, so that minus 177 is almost 0, basically. So with the perfect implementation of the loads, so the channel is almost perfectly diagonalized. So that means we obtain a very, very, very good approximation of the precoding matrix at the electromagnetic level. This is if everything is ideal. If we consider non-ideal, so some implementation error, obviously this gap reduces, so that we studied that if the implementation error are within 10% of relative error, then the coupling between the layers is still below minus 10 dB. Anyway, just a sketch on an improved model. So the previous model assumed the ideal rectangle elements, assume an ideal, so perfect matching network, reconfigurable perfect matching network, which is obviously not very realistic. So the model has been extended in order to consider more realistic, let's say, reconfigurable loads. For instance, use Varactol diode, so to mimic, let's say, a configurable reactive load. But here we have some loss because it's not ideal. And at the same time, it's possible to remove completely the matching network by adding the same Varactol diode here, and then trying to optimize jointly the DSA and the matching through these elements, so that we can remove completely the matching network, which is very complicated. And the numerical result indicates that we have almost negligible approximation loss compared to a perfect matching and loading, apart from the efficiency that move from 100% to 70-80% because of these losses, of the dissipation on the loads, and also because of not perfect, let's say, matching. So this is what has been obtained. Well, so finally, just a few words about the comparison between the SIM and DSA. As I mentioned before, SIM is very nice in terms of optimization, because we can use typical techniques from deep neural networks, but at the same time, so the model so far is quite poor, and also only the last layer radiates, so that the degree of freedom we have are those of the last layer, okay? Whereas here, the degree of freedom is of the entire structure, okay? And in general, the distance between the layer must be kept more or less some lambda, whereas here all the elements are spaced apart of about lambda over 4. So in other words, it is possible to obtain a similar performance using the DSA of the SIM with a more compact structure. In addition, the fact that all these elements contribute to radiation allows this structure to be also super directive, whereas here super directivity cannot be obtained. So there are some pros and cons of this structure. So in conclusion, SIM and DSA are very promising technologies to realize signal processing at the electromagnetic level in order to reduce the need for extensive digital signal processing in the baseband, and also to reduce the number of RF chain, and at the same time reduce the power consumption, and so on. In other words, to address the sustainability concern of future wireless networks. Obviously, this kind of structures cannot solve all the problems, and perhaps the most likely architecture we will see in the next future will be the following one, in which we have the signal processing task, which is subdivided between the digital signal processing, digital domain, the analog, classical analog domain, so phase shifter and so on, and the electromagnetic domain. So here the key question is, what is the best balance between the processing, the digital domain, analog domain, electromagnetic domain, in order to obtain a certain performance with limited complexity, limited latency, and limited power consumption. So this is quite an open question, but it's very interesting scenario. So there are several open issues. So one is the consideration of frequency selective effects. So there are some very preliminary studies on that, but this is still an open issue. Another problem is the design of more efficient optimization schemes. Geometry optimization, so what is the best geometry, for a given application for the scatterers? How to combine all this stuff with AI tools, or the other way around, how this structure can help AI, for instance. So these are another question. Implementation prototypes. So with our colleagues in work in the electromagnetic field, we are studying implementation of prototype of DSA in particular. Also, the adoption of advanced metamaterials can offer new opportunities. So metamaterial that can embed some processing directly in the metamaterial. So this is a very interesting scenario. And as I mentioned before, how to combine classical, let's say, architecture, digital analog architecture, with the electromagnetic signal processing. Okay, so so that close my talk. Let me stop the recording. If I find it, okay, this one.